in by factor of 10 and 100, right? So let's do that. Just multiply the gains by 10. And see the response. Here, remember, it's a sine wave with 1 hertz. If you see now, increasing the gain by factor of 10, the error is small in this case.
But the target error for us is something like 10 into 10 to the minus 3 or even lesser. So
yeah,
this one is still pretty big.
So we can play with another one.
Now just go ahead and show them the internal model control.
Okay. After that, after you play a little bit with the PID controller that you have before, now you go to and build another diagram. So it's gonna be the same. If you see, we just substitute the PID controller for our IMC. Well, you need to do write some code in order to get the numerator and denominator. In this case, let me show you right here. If you remember the K and tau of your motor, you need to use it in this case, or if you don't have it, if you are using different motor, you need to take again the K and tau in order to get a better response, right? So if you see, we have the angular velocity because we need it for the frequency. You can choose different lambdas. We're gonna use 5 different lambda in order to get the root. So if you see here, I have 3 different groups. You can choose whatever you want. This is the formula to get the root, and then after that you use the poly function in order to get a polynomial equation, and then you follow the rules and you get A, B, C, D, E, and F.
I mean, those come out from the solution when you compare your expanded version of lambda of s with the expanded version of A of s, and you compare the coefficients. You will get equations which he's showing you. He's plugged in his code to get A, B, C, D, E, and F.
So yeah, and after that you just place the A, B, C, the values that you have, and it's gonna be like that. So the numerator is gonna be C, D, E, F, and the denominator is gonna be A, B, and the third value is gonna be 8 times
omega squared.
Yeah, mega squared, and the fourth value is gonna be V times mega squared. And after that, you just run the code using the first value, the first 5 lambdas that you have. Then run the motor. Yeah. Again, I'm using 1 hertz. The frequency is 1 hertz. If you see, I'm running for 5 seconds. If you remember the PID controller that we use, we simulate with when we were using 1 hertz, right? It was really big, and if you see here, comparing to the PID that we simulated before, this is small.
Yeah. Can you do an auto scale on that? As you can see, the average value is around 10 to the minus 3, and it's even lesser. In fact, it's like 5 to the minus 3. So if you play around with your lambdas, you can get it to go even smaller.
Better.
Yeah.
Yeah, so let's play with another one. Let's see. Run the code. Okay. Build. Diagram again. And wait, see, the output is almost the same.
Yeah,
the input,
I mean,
and the error is really
yep,
small.
the error is like a peak of like 2 into 10 to the minus 3. This is really good. So as you can see, you need an internal model controller. And also about the 5, like you should test it at about 2 frequencies. So we'll do it at about say 3 hertz.
Yep.
The reason I suggest you do 3 or 2 hertz and not 5 hertz is because in my experience, these motors at 5 hertz, some damage happens to the gearbox due to excessive chattering. So it's not really a good idea to damage stuff. So he'll just show you one with the same poles at 3 hertz.
3 hertz?
Yeah.
You just need to change here. Run the code again. Build motor. Run.
Well, as you can see, as the frequency went up, the error goes up obviously because the speed of tracking has increased. But even then, the average value of this is like less than 1 into 10 to the minus 3. So it works pretty well.
It's good.
And now my friend is going to go ahead and show you the friction effects that we want to observe.
Okay guys, after that we're just going to see the friction to prove.
I mean, we're just going to see the effects of friction when we give it a very small amplitude input.
Yep. This is the amplitude. We're gonna use 0.005.
And we're still operating at 3 hertz. So the idea is to make your motor barely move. So I'll let my friend run it and I'll focus on the motor so you can see a small motion we're talking about. As you can see, it's just barely moving. There's some small motion. And now I'll show you the screen as to how the output looks. And you can see it's not really a sine wave anymore. It's got its top clipped off, it's like square, and there are disturbances. So that is an evidence of the friction, inherent friction that exists in the motor.
Non-linearity.
Yeah, that's an evidence of the non-linearity. It's good to observe that. You really get to see what you learn. And that's it for this lab.
Yep.
You can just save this data and make pretty plots out of it.
And compare between the PID controller and the
IMC controller.
IMC.
Well, thanks for watching. Bye.
Bye bye.